Good morning, everybody, and welcome to the second day of the workshop program. And today we have a little bit of a different program because we'll have several talks, and then when the coffee session arrives, we will actually have a panel discussion right here on the stage, and you will be able to ask our panelists lots of questions. And then we will continue with the program and the talks before lunch. So our first speaker today is Adam Foster from Aalto University, and he'll be talking about machine learning in scanning probe microscopy. So thank you, Adam.
Thank you, Melissa, and thanks very much to the organizers. It's good to see this meeting back after quite a gap. So I'm going to talk about machine learning, but I think my task was made very easy yesterday by Maria. So she introduced the whole idea about why we might care of using machine learning to solve problems in microscopy. And one of the boxes in her fantastic code was SPM. And she touched on it in a couple of slides. So I'm going to go into more detail in why we have started to use machine learning approaches, and not just us, many other people, in SPM. I'm going to introduce SPM because I guess most of you are machine learning people. I'm going to try and show what I think we've achieved and some of the challenges we still face. So I'm Adam Foster, as introduced, from very nearby. I also spend 1 month a year in Kanazawa pretending to know something about biology. So first of all, big thank yous. So there's lots of people from Aalto, not just my group. We've had a great interaction with the local experimental group, particularly Peter Lilleroth. And I will talk about why this is actually essential going forwards. And similarly, we've had very good interactions with local computer science people. So we're physicists pretending to do machine learning, and they are machine learners, not very interested in physics, to be honest. But that combination of interaction between theory, experiment, and computer science, I think is really at the heart of what we've been doing, and I've really enjoyed it. And a word out to the people who pay, so thank you. So first of all, let's do a little bit of quick machine learning and put seeing atoms into Google. Of course, this is a bias search. This is my Google. It still doesn't give any of my work, which is very disappointing. But if you put seeing atoms into Google, you'll see this type of image or set of images. And nearly all of these are from microscopy, either electron microscopy, which Maria talked about a lot yesterday, I'm not really going to talk about today, or scanning probe microscopy. So these are the experimental tools that we use if we want to see atoms. I'll talk about what that really means later. But as an atomistic simulation guy, this interests us because this is an arena where we can really test our models. So we cannot just develop our theories in isolation. If we develop an atomistic picture, these people are seeing atomistic pictures. It's really against the spirit of science not to try and put these two things together. But this is not always very easy. So I say scanning probe microscopy, this is a huge field of techniques. You could argue starting perhaps in the early 80s with scanning tunneling microscopy, which we saw a little of yesterday, STM, where you're imaging conducting materials, measuring the tunneling current from a tip. And this has atomic or even beyond orbital resolution of materials if they conduct electrons. Surprisingly, often in terms of material science, the sister of this, atomic force microscopy, is actually much more widely used. This is the techniques that's used in biology and biological physics for looking at materials at larger scales. But I'll show that it also can be brought into the realm of atomic resolution with some advances in the last 20 years. You can do a lot more than just these. I'm going to be talking exclusively, more or less, about measurements in ultra-high vacuum at low temperature, where the science is easier, but you can do things in different environments. You can do measurements in liquids, buffer solutions. You can do measurements while interacting with light, use electric fields. And at the end of the day, the question really is, what are you seeing? So you'll see fantastic spectra and images, and it's our role to try and understand whether the experimentalists are really seeing what they think and whether we can find new science from those measurements. So this is a machine learning meeting, so I'm going to go straight into that and also try and introduce in one slide the history of machine learning and scanning probe microscopy, which of course is skipping a lot. But it is really coming increasingly the last 5 years. I've seen a massive increase in the applications of these techniques. I'm picking some examples which I like, maybe some of the earliest high resolution approaches coming from the Bob Woolco's group in Canada, where they have tip control. So they're trying to build molecular circuits using dangling bond wires on a hydrogen covered surface. So you remove hydrogen from a hydrogen covered silicon surface, you get dangling bonds, you can make wires, you can make circuits. And so they're trying to build this, and they very soon realize it's pointless to try and do this by hand. It takes forever. So they designed an autonomous algorithm, which later involved machine learning, that the machine will find areas with low defect density and make some dangling wire structures that you want on the surface. And this is still going on and improving all the time. Some of the first ideas, particularly of recognizing whether your tip is good or not, recognizing defects in the surface. Perhaps one of my favorite ones is this, where they basically went and got a huge amount of old STM data that nobody could be bothered to look at because it was so noisy and rough. They couldn't find anything useful, and ran it through a pattern recognition technique using deep learning, and were able to find different signatures of quantum order in these oxide images of oxide materials. So I think this is very sort of tantalizing idea of turning bad old experimental unpublished data into really high impact, high level science. So don't ever throw anything away. I don't think there's too many experimentalists in the audience. Coming from Sergey Kalinin's group in the States, I guess he's now temporarily at Amazon, they've been pioneering the idea of bringing the whole machine learning infrastructure into SPM. And this is a recent example, which I really like, and really on the topic of this meeting, active learning, where they're doing piezo force microscopy, one of the family. We don't need to go into the details, but the idea is you do a large scale image, which shows you've trained the machine to recognize the characteristic features in that image, which are likely to be scientifically interesting. You then zoom into those points and do spectroscopy only at those points, maximizing the return on a given very difficult and time-consuming experiment. And this touches, I think, on some of the other talks we've seen in this meeting. And this is a similar approach now in biophysics. This is AFM imaging some, I think, DNA structures on a surface, doing a large-scale image, training a machine learning agent to recognize those features. I don't know why the blue one is particularly interesting to the biophysicist, but recognizing the structure that is of interest, and the machine will autonomously, without user input, zoom in on that region and get a much higher resolution image in that area. Okay. I think yesterday, Maria, in talking about STM, briefly touched on the role of, I'm going to say with speech marks, parameters in SPM imaging. I think this is a very nice way to condense almost my whole career into one word of understanding these parameters. And the most important parameter right from my PhD was the tip. So if you're imaging things in atomic resolution, it's actually the nature of this last atom, let's simplify it, last atom on the tip that really matters. And we spent a long time as theorists trying to understand the role it plays. And there was a breakthrough in IBM almost 15 years ago now, where they were able to pick up one molecule with a tip, controllably, reproducibly, and then using this molecule, they're able to obtain these really high resolution images in atomic force microscopy, where you basically are seeing the, let's say, the electron density of the system. So you see where the atoms are. In principle, you see where the bonds are in the material. And this was soon partnered by simulation tools, which were very good, that we could get really good agreement between experiment and simulation at very minimal computational cost. And of course, it's my talk, so I can pick one example from our research. Here's just an example of a molecularly assembled material where, well, if you don't know, you could tell me which one is a simulation and which one is experiment. That is the point. The agreement is excellent, even for this, I would say, fairly complicated self-assembled material. But the point is, if the simulated data is that good, we can actually use it as synthetic data in machine learning. Because most often we're not interested, or at least I am not that interested, in the simple systems like this flat molecularly assembled material. What happens if we have very complicated molecules which are not necessarily flat, which have not been carefully synthesized? This is actually an oil just thrown on a surface at IBM. What actually are all these molecules? Is there anything interesting or not? And as we move into this complicated system with less information, more configurational challenges, bigger systems, for example, here is a biomolecular. Okay, I'm too loud. Okay, it reminds me of karaoke. Here we have a dehydrated DNA on the surface, and here this was too big to even try and do simulations, so people just put a molecular structure on top of it and guess. So we basically cannot use our old approaches to solve this problem. We need some new approaches to give us a first step. We have all these wonderful tools, DFT and beyond, to solve problems, but how do we get a first order idea? What data goes into the simulation in the first place? So I'll go through this briefly. It's already a few years old now. So we took the idea of, with the quality of this simulated data, let's build a database of AFM images. So we took one of the standard molecular data sets and we imaged this. And here is an example of how we build this data set. You're taking this molecule, you're imaging. Here we see 3 different images at different heights. So height is a big parameter in AFM. Images change as you change the distance between the atom and the tip. The database has many more than 3. I just show 3 here. And for each of those configurations and heights, we predict a molecular fingerprint, or the range of height leads to a molecular fingerprint. And our idea is, if we can train machine learning to learn these fingerprints, we can then feed into the machine learned model experimental images and spit out information about what we think the experimentalists are seeing. And of course, as mentioned yesterday, you soon learn you need to augment the simulated, beautiful simulated data with lots of noise, but I sort of skip over that. Quickly, just to show how well it works, of course, for simulated data, here's a few examples. Here is a buckyball. You see the prediction at a bunch of heights for the fingerprints. You see the reference. Here, slightly more complicated, more 3D shape, different functional groups. Again, pretty good. At this early stage, we even had preliminary elemental recognition. I'll come back to this later. But this was a like proof of concept that this actually could work to give us a beginning point. So the success, or the initial test of this, of course, was take experimental data. This was with the groups here. We took a bunch of, this is the camphor molecule, which you can see in the middle there in this molecular configuration. The idea is, if you throw this onto a surface, a bit like a wobbly football, it will occupy lots of different configurational states. And the experimentalists then made a heroic effort to measure all these different configurations. I showed just 2 here. And the idea on the left here, we have each row is one experimental set. And we have 3 experimental images and examples showing different heights. These are fed into the machine learning. We predict a fingerprint. We match this fingerprint. And at this stage, we brute force then to guess the configuration and calculate a simulated image on the right. And if everything's gone well, which it reasonably did in this case, the images on the right should look like the images on the left. So this was proof of concept that we could go from not knowing much to actually having an idea of where we can then apply more complicated methods. And there is some nice work also from Patrick's group in going into the real details of configurations. But you've sort of gone from no idea, let's do 1 million DFT calculations, to we've got a pretty good idea, let's do 100 DFT calculations. We push this forward. You go back to the training. In principle, you also include the heart tree potential calculated from DFT. in the images that you generate. So why don't we try and learn that, learn the electrostatic potential? Can we, predict more data based on our training? And yes, we can. We can nicely predict electrostatic data for given molecules to reasonable quantitative accuracy. And again, this is very nice. If you're interested, you have images of a big a biomolecule, you're interested in where the functional groups are, where the dipoles are, you can get a really fast, this is seconds on a laptop, prediction of the electrostatic potential that you could trust to a reasonable degree. It's gone slow. Okay. I mentioned that the problem with the fingerprints is that they give you an idea of where atoms are, which is already quite good. But if you want elemental information, they prove to be not perfect, although there's some work in Spain that gives ideas to go beyond that. But we took a slightly different route and thought, actually, what we really want is X, Y, Z coordinates of the system. So why don't we train a graph neural network to predict that directly? So this is what we trained. Exactly in the same way, we have the trained database, which goes in the node and edge positions of our graph for a given simulated image. And then we can feed in experimental or simulated AFM images and make a direct prediction of where the atoms are and what is their elemental character. And again, this works very well. And I'm going to show you a real example very briefly or shortly that we can go directly from experimental images to a very good, very accurate, 80–90% accurate prediction of what the molecule is and where the atoms are in it. Okay, so that was in a way the method from that side. So now I go to our first, let's say, real challenge, like trying to find something we didn't understand. And here we have had a long interest in ice surface interfaces, particularly if you're someone like me who lives on a hill in the winter in Finland. It's not very fun going down it. So friction matters, cloud formation, the growth of ice on surfaces has long been a very interesting and challenging problem. And again, SPM has come, I'm not going to say to the rescue, it has arrived to look at these materials in high resolution. And there's some great work coming from China, looking in real detail at how ice forms, particularly, at least in this initial work, these 2D structures. So almost like looking at an ice surface grown on metal surfaces. And that, you can really see where the atoms are and see where the hydrogen bonds are. This builds in a way of earlier STM studies where people looked at small ice clusters on metals and tried to understand their properties. But we were again thinking, okay, the real challenge is what happens to ice as you keep growing. You go beyond these simple 2D structures, you get into amorphous structures, you get larger structures, what the crystallization point, the nucleation point. This is where the challenge comes, that it's very difficult, almost impossible to take this sort of simple, we know what the surface is, or we can guess 10 different surfaces and calculate them with DFT. Can we bring our method in to try and solve this problem? So the first thing we did was took the original method, which has no training on water, no water in the database, and does it work at all? And it wasn't bad. So we feed in the experimental data, exactly the same type of experimental data before, but now they know the system is water. And we basically asked it to predict where oxygen and hydrogen is. We get a reasonable guess. There is something that you can see there's bits missing. We can take this and in a way use our intuition as scientists to fill in the gaps. We know hydrogen cannot exist on its own. So you can add in the missing water molecules. You can calculate then the AFM. And if you turn your head, you can see that this AFM images from simulations match very well. You can also do the STM and actually see that maybe those original STM data was missing a water molecule or two. Okay, fine. But this wasn't brilliant. So it was always immediately clear, as everyone in this room knows, that it's not great to use a model that's been trained on something that it's never seen. So we retrained a model using configurations of ice on metal surfaces. And this is already an order of magnitude more expensive to calculate. The original data set with DFT is molecules in vacuum. Now we have a surface, much more expensive. So once we got up to hundreds, approaching 1,000 points, we thought, is there a way we can actually expand this database without having to do endless DFT calculations over and over again? If we've already got 700 DFT calculations, maybe we could train a neural network potential so we can generate as many configurations as we want. That's what we did. We tried a few out. Lots of people here are experts in this. But in this case, we used the encrypt potential, which gave us this advantage of not needing so many configurations to get an accurate potential. Needed much less training data. And we compared this. We had a classical potential, which we were already very unhappy with. It was clearly not giving us good configurations. With our neural network potential, I mean, I show the sort of tabloid version of the error. So I have nice plots showing how the error is much better with the neural network potential. But here we're just comparing the forces versus DFT, and you see the error in the classical force field for a given configuration versus that with the neural network error. So now we can build thousands or add thousands of ICE configurations into our machine learning and train the model to recognize how ICE behaves. And this is a big slide, but the idea here in the top is a sequence of seven or even 8 experimental examples, the experimental data. And this is one snapshot from a range of experimental data. And already in general, as an expert, maybe 1 or 2 of these you could guess by eye where the water is, but we just feed this into the new model. It makes a prediction of what the water structure is, and then we can calculate the simulated AFM image, and generally this is in very good agreement. And now we can take this, and we're just in the process of doing this, we can take this image, feed it back into DFT, and validate, or at least get maybe 10 configurations per ICE cluster, and actually tell what they're seeing. And this becomes a way, again, in seconds on a laptop, you can take a complicated structure from AFM and make predictions about what they're actually seeing, even in real time. Okay. And just to end with, as you can imagine, we're making a lot of demands of the experimentalists in this way. So can we do something to help them? So I already showed earlier work of people controlling the tip in STM measurements. So we actually worked with the local experimentalists, control the tip in AFM measurements. So there is some challenge in going and picking up one of these CO molecules. And then it's very important, or it helps a lot, if the CO molecule is absorbed vertically on the tip. So we developed a deep learning framework that would pick up a molecule, scan other CO molecules on the surface, make sure you have a nice symmetric spot, the so-called good tips. And if not, it goes away, voltage pulses that molecule away, picks up another one, goes back. So this is the idea that the experimentalists can then enjoy their Sunday night and come to work ready to measure on Monday morning. We took that a little bit further and tried the idea of now autonomously doing something in AFM that is tedious to do for the experimentalists. And here we're going to move to reinforcement learning. I guess many people in here are very familiar with this idea, this branch of if you split machine learning into 3. So we have supervised learning, which is mostly what I've been talking about before, unsupervised learning, often classifying data. We've seen examples here. And reinforcement learning, which of course has become famous in the concept of robotics. So this is the idea that you train an agent with rewards or punishments to do a task, and gradually it learns to do this task very efficiently, unlike this robot arm here. But already in my mind, when we saw this robot arm, it's very easy to reimagine this as a scanning probe microscopy tip trying to move atoms on a surface. This is, of course, atomic manipulation has been done before a lot, very famously in many cases. So this is the cool video from IBM, where they actually had a professional director, and this is a boy playing with his atom. So I strongly recommend watching it if you want to see well, I guess it's not taxpayers' money being wasted, it's corporation money being wasted, but it's extremely fun. In terms of science, the original manipulation paper from Cromie back in 1993, where they moved atoms into a ring forming this quantum corral, and you can see the quantum electron surface states inside this ring, which was fantastic and one of the most famous nanotechnology, nanoscale images of the past. More recently, people have built electronics. So they build electronic circuits with atoms and molecules, manipulation, test physical ideas. So here they've built a Boltzmann statistical machine on the surface. So we said, could we do this, but now take away the pain, at least from our perspective as theorists? We assume experimentalists don't want to waste their time with repetitive tasks. Could we do this with a machine learning agent, a reinforcement learning agent? We sat down with the experimentalists, they were interested, and of course we picked the simplest possible system to start. So this is a proof of concept. So we take a silver surface and we're going to add atoms of silver on that surface with a silver tip. So we've tried to remove as many of these parameters as possible. The machine has control of not everything, especially in the beginning. We are trying to protect these €1 million instruments, but it does have a lot of control over height, tip position, bias, the voltage applied, and the conductance it measures. So we kind of don't tell it much. We just say, probably this is the range that you should look at in the beginning. The big problem always in this is, and this is where the human aspect is also slowed down, is taking an image is very slow. So if every time we attempt to do something in our reinforcement learning, somebody has to have a look at an image and go, did it work or didn't it? This is just hopeless. And we've made their life more complicated. But we can look at something else. We can look at the tunneling current, the conductance. So this is an example plot. The blue line here is where no atoms moved, and the red line is where atoms moved. It's not as simple as that you see a spike and an atom moved, unfortunately, but that's why we came up with an algorithm that generally an atom has moved if there's a spike, generally. So we trained a CNN to recognize this characteristically, and this got up to about 80% when we finally sort of our last version of this CNN. And we also combined this with a simple formula which looked for a big gradient change. So it looks for spikes. So this is the human element. And so then basically the deep reinforcement learning training, it will perform a scan of the surface. If the CNN says there's been a jump, if the algorithm says there is a jump, at the end of an episode, of a training episode, or with a random probability. I think this random probability is the fear the experimentalists that they don't trust it, and it started much higher and gradually went down. And here on the right, you can see some examples of it moving atoms around, the initial positions and the jumps. But the most important thing for us was coming back to these parameters. It's absolutely clear if you're taking a tip and interacting with atoms, add atoms on the surface and everything's silver, you're going to pick them up every so often. There's just no way it's not going to happen. And if every time you pick up a tip, we have to go right at a new atom on the tip, we have to go right back to the beginning and start training again, this is never going to work. But actually this shows the training, basically the rewards, so the increasing reward and the reducing error. And we see these spikes, we've labeled them here. We know from the images when these tip changes happen. And the machine basically doesn't have to start again. It recognizes there's been a tip change and adjusts the parameters, moves a little bit further away from the surface and carries on. So here on the left, you can see an example. We're putting the target. It's moving towards the target reproducibly. And on the right, we have our final structure. This is a 42 atom array built on the surface. And this took 66 from the fully trained reinforcement agent. It took 66 steps and about an hour. And we think we can make this an order of magnitude faster by really pushing the parameters. In truth, we're not going to do that because we're already bored with silver on silver. And now we're actually moving towards manipulating things that are very interesting scientifically. For example, building large spin arrays and looking at the physics of these without having to spend 2 months building it atom by atom. Okay, I end here with the first conclusion is kind of obvious for everybody in this room, that machine learning is not magic. This is more important with a general audience, but perhaps to you, for our experiences, first contact with experimental data is really harsh. And we have to almost begin again from scratch in understanding how the data is different in experiment, and trying to include all the concepts that, of course, the machine learns the errors and the artifacts as real parts of the science, which they are not. We also like to think of machine learning as another tool in our computational physics box. It's never the end of the story. It's a way we can accelerate getting to the answer. So we really like combining it in workflows, as many other people do, with DFT, with MD, with Monte Carlo. This is the way you can get to the answer faster. We don't have to throw away all those things we grew up learning. And lastly, in a nod towards my Japanese affiliation, you can take all these ideas and take them into more complicated environments away from this UHV low temperature regime, and actually do things in liquids, in biologically relevant areas, but the experimental data is much more noisy, you have much less control. So there you have to think more realistically about what you can achieve, and doing things fast and giving qualitatively coarse grain predictions from machine learning is maybe more important than telling me exactly what atom they're seeing. Thank you.
Thank you, Adam. Great opening for today's program. Do we have any questions? Okay, maybe Kunal first. Thanks.
Thanks a lot for the fun talk, Adam. We all know that reinforcement learning algorithms are plagued by high variance, right? So when you're training the algorithms, depending on a variety of different factors, the rewards can be highly varying, like the plots that you showed.
Yeah.
So when you had limited amount of data, did you have problems with that? Or what was your experience with using reinforcement learning algorithms and their high variance in this kind of a setting?
Yeah, I mean, you're talking about the very beginning of this, where we had nothing. I don't know, I don't think we had so much trouble, but I don't know whether this is a factor that with that system, the experimentalists from the beginning, I mean, they knew how to move silver on silver. So maybe they gave us a gift and said, you know, okay, guys, you think your agent's great, but let's just keep it in these parameter spaces. So I think the real challenge is what we have now. They actually have a system which they failed to manipulate several times. More complicated system. We ran the agent on it, and the agent did something, we don't know why, but not that well. And we actually think the reason is because it's still got this constraint. So it's been told how to, you know, you can only do this because that works on silver and silver, but it doesn't seem to work. So now we're going to open it up, and then we might exactly have this problem, this variance. So of course we picked an easy example to prove the idea, but I think so, yes. And the other thing is that the tip changes there are, okay, you have a silver tip and we've picked up 1 or 2 silver atoms, fine. If we're imaging a 2D material on a superconductor, there's all sorts of nasty crap we can pick up, which is not going to be just making the tip, it's going to completely change it chemically. And this is going to be a challenge.
Thank you, Adam, for the very interesting results. I had a question on the ice flakes or the ice clusters. So they're really tiny, right? So they're not yet sort of very regular ice structures.
No.
So when you said your plan was, or you may be already doing it, to image in real time and have this real time identification. So is your recognition model, is it continuous? So if the cluster evolves in real time, does your prediction sort of continuously evolve too, or do you get some artifacts?
No, this we don't have. So the model is like fixed.
Yeah.
So this would be an interesting aspect to bring this back in. But we have there's some interesting challenges, like in these clusters, which are not this simple 2D. They even have hydrogen atoms, which are not, you know, Born-Oppenheimer breaks down. and they hop. And so DFT is wrong.
Right.
So AFM might be right and the machine learning might be right, but then our validation, let's step, the DFT is wrong. We would have to go and do some, Metropolis, Monte Carlo, something to actually find it. But this is where I get interested, that then you start to care less about the DFT maybe and trust the machine learning in this cycle.
Yeah.
But it would be very good to have this active approach that we actually learn on the fly. I agree.
Yeah.
And with the neural network potential, we have the speed to do this.
Yeah. Can you actually incorporate these quantum effects into the neural network if you train with like path integral MD?
Some people have. I think the actual ICE experts have been playing with this, but it seems to make things very slow. So I mean, the high level neural network potential for this ICE, I think, was only 2 or 3 times faster than DFT.
Cool.
So, but it's cool. It's better than DFT in this sense. Yeah.
Any further questions from Adam? I have one actually about the artifacts. So you've helpfully shown that machine learning has really helped now to get very high grade images and very comparable to experiments, great for identification. We've overcome so many obstacles. But one obvious thing that has always plagued SPM is that they encode so many artifacts and it's harder to extract the real information underneath.
Yep.
So we've been going down the route of just guessing the model and then reproducing all those artifacts to make it comparable. But can we actually remove the artifacts from the experimental images, and how? What are the methods that are now being considered for this?
We're trying this because there's so many in the imaging in liquids. It's insane. So what we're going to try and do is they have made a huge effort to give us a ton of experimental data. So instead of taking the simulated data and making all this artificial noise, we might try and learn from the experimental data what is real and what is not.
And try to denoise.
Yeah. But that's all I'll say. But it's just starting. And you need so much data and it's not easy for them. You know very well in this high resolution, it's not easy. So the other thing is we try and persuade them to let us have autonomous control. And can't we run all weekend while you're resting? But the Japanese say, of course, are not resting at the weekend.
Okay, so next time we hear more about this from you. Thank you very much. Oh, there is a Zoom question.
Oh, okay.
Great.
Okay, so question from Gergely Juhas. Can you include somehow atomistic models into the reinforcement learning to control on new surfaces?
This is a very good question, actually. One thing we are trying now is to tell something to the experimentalist in the sense of, because touching back to my first question, we're a bit skeptical that the agent will just be able to handle everything without having a clue. So we're now actually working on neural net potentials for the whole manipulation process. For a given surface, a given molecule, and a given tip, you could learn the interactions. And then we can try and predict paths. I'm talking to you, Jari, like you asked the question. But so the answer is yes, and that is a route. But it's also then we're starting to reach the state of the art in the neural network potentials. And we have an issue with conductance, how we can include that effect, and electric fields. And of course, we cannot also be a state of the art developer of these neural networks, so we have to interact with the people who are and use this. But I think there's a lot of scope. Does that answer your question? Yeah.
Thank you, Adam. So let's thank Adam again. And our next speaker is Xin Yang. If you're here, yep.